Welcome and girls. In today's video, we will discuss about the different gas concentrations in the atmosphere, and later we will discuss about the sophisticated phenomena of lapse rate. Okay, so let's start. In our atmosphere, these are the major gases in the troposphere, to be exact. Nitrogen is found in the atmosphere at 78%. That means upon the 100%, 78.084% of it is nitrogen, dinitrogen N2. You might ask me why am I writing in the 3 decimal points. The questions might be asked in the NET exam to be specific about the concentrations. So there is a chance that it can be asked in 3rd decimal point. Okay, so dinitrogen makes up the lion's share of gas in the atmosphere, which is 78.084%, followed by our life source, oxygen, dioxygen, 20.947%. It is the exact amount. Some papers will tell you 21%. So to be, it is the rounded version of 20.9. So the exact amount of oxygen in the atmosphere is 20.947%, followed by argon. So keep this in mind. The third most abundant gas in the atmosphere is argon, not carbon dioxide. So argon is present in the atmosphere up to 0.934%. Some books will tell you 1%. It's a rounded figure of 0.9. So to be exact, argon is present in the atmosphere up to 0.934%. You should keep in mind that all these gases that I mentioned here is with relation to troposphere, not to stratosphere, not to ionosphere, not to mesosphere. Okay. So the fourth most abundant gas in the atmosphere is our most discussed villain, carbon dioxide, 0.04%, followed by dihydrogen oxide, which is also called as water. Water is present in the atmosphere in the form of water vapor, and their concentration in the atmosphere is variable. We have discussed this phenomena in our previous video when we discussed about greenhouse gases and the global warming effect. So followed by neon. Neon is a noble gas, which means it won't react with any gas in normal circumstances. It won't react with any of the elements in the periodic table. So neon is the gas which is in the 6th place. So neon is present in the atmosphere up to 0.0018%, followed by helium. Helium is again another noble gas present in the atmosphere up to 0.0005%. And here comes our next villain, methane. Methane is a villain with relation to greenhouse gas effect, and it causes global warming. Okay, so methane is present in the atmosphere from 0.00017%. Okay, so these are the major gases in the troposphere and their exact concentration up to 3rd decimal point. So coming to lapse rate. Lapse rate is simply the decrease in temperature when the elevation increases, or the decrease in temperature when altitude increases. Okay, so that is what is called as lapse rate. And lapse rate is of 3 or 4 types. Among them, the first one is adiabatic lapse rate. Okay, ALR. According to ALR, if consider this the land surface, okay, and this is an air parcel, okay. When this air parcel goes up, its temperature decreases by 1 degree. So 1 degree Celsius. 1 degree Celsius by every 100 meter. Then that is adiabatic lapse rate. So if an air parcel with respect to its surroundings, if it goes up by a distance of 100 meter, if the temperature decrease in that point from 100 meters above the surface level, if the temperature decrease is about 1 degree Celsius, then it is called as adiabatic lapse rate. I hope that it is clear. So if the temperature decrease when we go up by 100 meters, it is 1, if it is 1 degree Celsius, then it is called as adiabatic lapse rate. Okay. So normally then if it becomes 1000 meters, then the temperature decrease would be 10 degrees Celsius. Okay, simple maths. So with respect to adiabatic lapse rate, the temperature decrease is approximately 10 degrees Celsius when we go up by 1 kilometer. Okay, I hope that it's clear. Now the second type, it is called as dry adiabatic lapse rate. It is a variation of adiabatic lapse rate itself. Okay, so and dry adiabatic lapse rate would be normally similar to the adiabatic lapse rate decrease, which is by the temperature decrease for every 100 meter would be 1 degree Celsius. Okay, right. Now the third one, wet adiabatic lapse rate. This is where all the confusion is rising. In wet adiabatic lapse rate, the temperature decrease by about 100 meters is about 0.64 degrees Celsius. Okay, so consider this as the land surface and we are measuring wet adiabatic lapse rate. So if the air parcel that we are considering is going up by 100 meters, the temperature decrease would be about 0.64 degrees Celsius. So if you are going up by 1 kilometer or 1000 meters, the temperature decrease would be 6.4 degrees Celsius. Okay, I hope that this is clear. So with relation to lapse rates, there is atmospheric lapse rate, and among them a dry adiabatic lapse rate is there, then wet adiabatic lapse rate is there. So these are the types of adiabatic lapse rate. Okay, so we can just write it like this: adiabatic lapse rate, dry adiabatic lapse rate, wet adiabatic lapse rate, then there is environmental adiabatic lapse rate or environmental lapse rate. So these are the different kinds of lapse rates. Okay, these are the different kinds of lapse rates. And so dry adiabatic lapse rate is about 1 degree Celsius for 100 meters, and for wet adiabatic lapse rate it is about 0.64 degrees Celsius for every 100 meter. Okay, so now with relation to different types of lapse rates, the stability of the atmosphere can be decided or predicted. Consider dt by dz. Okay, consider dt by dz, and this is environmental lapse rate. Okay, dt by dz is simply temperature decrease. dt is the temperature decrease. Okay, and dz is the elevation increase. Okay, so since these both guys are inversely proportional to each other, in the lapse rate it is inversely proportional to each other. Okay, So the change in temperature is dT. The change in temperature by elevation is called as dt by dz. So dz is the change in elevation, dt is the change in temperature. So dt by dz is the change in temperature with change in elevation. Okay, and so this change in temperature and elevation we consider it as environmental lapse rate, and we take another scenario where dt by dz or the lapse rate is in the condition of dry adiabatic lapse rate. Okay, we have discussed about what these two guys are. Okay, and substitute that in here. Okay, so if these two guys are equal, which means environmental lapse rate and dry adiabatic lapse rate is equal to each other, they have the same value. If this is the case, then the atmosphere is considered to be stable. To be exact, it is considered to be neutrally stable, because consider this as the land surface and this air parcel is the point of concern. So this is, consider this as the dry adiabatic lapse rate, DALR. Okay, DALR, and consider the surroundings as ELR. Okay, so if when this dry adiabatic lapse rate goes up and this air parcel, when this air parcel goes up, its condition is dry adiabatic in origin. Okay, and if this air parcel has the same temperature as the environmental lapse rate or the temperature in its surroundings, then the atmosphere will be stable. That means there won't be any winds, there won't be any storms. Such condition is called as stable or neutrally stable. Okay, this is the first case.